Okay, so we are going to look at our work energy theorem practice problem number 1. And that practice problem reads, an asteroid has a mass of 4.5 times 10 to the 4th kilograms, and a force causes its speed to change from 7,100 meters per second to 5,500 meters per second, slowing it down. What is the work done by this force? And if the asteroid slows down over a distance of 1.8 times 10 to the 6th meters, determine the magnitude of the force. So I know we haven't really dealt with these large of numbers before. I will walk you through that process a little bit. The physics is the same. We want to make this problem a little realistic with asteroid lengths and distances and speeds. So that's why we're using those big numbers. But they're just lots of zeros at the end of those first two numbers. So let's first just frame that problem. We have an asteroid, and we know the mass of that asteroid is 4.5 times 10 to the 4th kilograms. So as a reminder of what this 10 to the 4th means, we move that decimal place over 4 times. So 1, 2, 3, 4 kilograms. So 45,000 kilograms. I will work in what's called scientific notation for the practice problem just because it gets to be a lot of zeros, but that's what that means as a reminder. It tells us that its speed changes, so it has some initial speed of 7,100, so 7,100 meters per second. Sorry, that's an initial speed. And it has a final speed of 5,500 meters per second. So it goes from 7,100 slowing down to 5,500. And if an object's speed is changing, its kinetic energy is changing. And if the kinetic energy is changing, work is being done by a net force. So we can use the work energy theorem to figure out how much work is being done. So we want to remember that the net work is equal to our change in kinetic energy. And we've been just using K, but just as a reminder, you sometimes will see that KE. So our change in kinetic energy, which we want to keep in mind, is our final kinetic energy minus our initial. Anytime we have a delta, a change in, it's final minus initial. So our work is 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared, or speed, because we want to keep in mind that kinetic energy is a scalar quantity. So speed there. Okay, so I can do some algebra to make the problem easier. I can just start plugging in numbers if I want to, but I'm going to pull out the 1/2 m, which is in each of those variables, v final squared minus v initial squared, since my masses are the same and the 1/2 is the same. And now we can solve for the net work. So we want 1/2. The mass is 4.5 times 10 to the 4th times 7,100 squared minus, oops, that's the initial, 5,500 squared minus 7,100 squared. And when we solve that, we end up with a work of 4.49 times 10 to the 11th joules. So 4.49, moving that decimal place over 11 times. A lot of zeros at the end of that, 9 of them, joules of work. And it's negative, which of course tells us that it's slowing it down. The work is working against the motion. And that's exactly what we see. So work is negative, the force opposite the displacement. All right, so that's part 1, recognizing that we have a change in energy. Change in speed gives us a change in energy, or the result of a change in energy. That's due to work. And the work energy theorem then, which is the net work, is equal to the change in kinetic energy, can be used. So now the second part of the question says, well, if the asteroid slows down over a distance of 1.8 times 10 to the 6th, what's the net force acting on it? And so we remember that our work is equal to our force times that distance. Our work 4.49 times 10 to the 11th, that negative tells us it's opposite, which means our force should be opposite. Remember, this negative means opposite, not left or right. Opposite the motion. Force parallel, and then we have, forgotten it already, 1.8 times 10 to the 6th meters. And so solving for our force, we get 2.5 times 10 to the 5th newtons. It is negative, and we want to keep in mind that that negative force means opposite the displacement. It does not mean negative direction like we've been using it before. All right, so recognizing work was done, and then applying what that work is a force through a distance, and recognizing that that negative means opposite the motion. Good job.